Okay, so good evening, everyone. With this, we start our third tutorial session on the NPTEL course on Foundations of Wavelets and Multi-Rate Digital Signal Processing. So in today's class or today's session, we will be reviewing whatever was covered in the module or week 3 of this course. Right. So in this week, we had learned about the equivalence of functions and sequences. And then we moved on to understanding what direct sum implies. Further on, we went on to discussing about filter banks and how they are used in analysis as well as synthesis in Z domain, which happens to be an analog of something very much similar to, uh, like not exactly similar, but it's like something which is analogous to what we do in continuous space, right? So if we do something called as a Fourier transform, it's somewhat analog in terms of its meaning in the discrete space. Okay. So this is what has been taught so far in the module 3 of this course. And now we would move on to revising all these topics. Also, I plan to start MATLAB analysis of certain signals or wavelets, etc. in the MATLAB software. Okay, so we begin with the equivalence of functions and sequences. In mathematical sense, we even call functions as sequences as well. Say, for example, we have a sequence of functions which, in a sense, uh, are they try to approximate some discontinuous functions, right? As an example, let me just talk about it. Say we have a Haar wavelet, right? It has a unit length. It's supported on a unit length, t, right? And then it takes a value of +1 and -1, and there is a discontinuity at half, right? So of course this function is discontinuous, right? So this Haar function is discontinuous. Now you recall that since however, what we can say is that this function happens to be a limiting case of course, there can be infinite such functions, but you can always have a function of this type. So for example, this type, right? This function is a continuous function. And of course, let's center it at, again, we have to center it at half, right? So this is 0, 1. This is the t-axis. So it has a value of +1, and at t is equal to 1, it has a value of -1. And now let's try to understand, okay, what's can we have a function can we obtain the Haar function as a sequence, right? So this is some sequence, say Fn, and this is the final function f. And Fn are all, this sequence of functions are all continuous in nature. However, this Haar wavelet happens to be, or let's adopt the usual notations. So let's call this as phi n of t as a function of t and phi of t, right? And this has this very strict value that it has 1 for 0 t less than half, and -1 for half t 1. So we see that at half, it doesn't have a definite value. So there is a discontinuity at half. So let's start. We can call this as a, say we can construct a function of this sort of property that it has a value of 1 at 0. So we can think of some function like e to the power minus 1. Say for example, we can think of some function there. So let's just try to hook up something. So this has a property of being plus 1 at t is equal to 0 and minus 1 at t is equal to 1. Okay. So in this scenario, there are certain possibilities, right? So what we will do is um, so say center something at e to the power minus say at t minus half, right? And if we say I'm just trying to cook up, right, at this moment. So say we have of course this is never possible, but let's still try to analyze something of this sort. Uh, Now, if we take a thing like, for example, you have 10 hyperbolic function, right? So 10 hyperbolic function of say x. Let's just try to cook up something. Let's see how it looks like. So 10 hyperbolic has a value of 0 because this is given by e to the power x plus e to the power, minus e to the power minus x divided by e to the power x plus e to the power minus x. Now at x is equal to 0, it exactly cancels out. I mean, the numerator becomes 0. And at x is equal to a very large number, right? So then x tends to say infinity. At x tends to infinity, you have value of 1 plus 1, and at you have minus 1. So this, like, taking this as an what do you call as an inspiration to construct our function. Now in this scenario, one way of doing it is, let's try to construct something of the sort of tan h of t is equal to say e to the power x or e to the power t by n minus e to the power minus t by n divided by e to the power t by n plus e to the power minus t by n. Now let's try to check whether this has the values that we would want it to have. At t is equal to 0, you have tan h 0 is equal to 0, right? So that's fine. However, what you see is this is also parameterized in terms of n. So this is parameterized as t, of course, and n, right? So here, yeah, I think I'm making some issues here. Let's still try to figure out some, if we can construct something like this. Right? So let's see something if we can. So we want, the thing is, okay, we are parameterizing it with respect to some n. N happens to be the index of the function, or the parameterizing in which that we are doing, and t happens to be the continuous variable that we would want to have. So that is our goal here. So yeah. So in this case, what we can do is we would want to center this function at p minus half, essentially, because all that we want is that. So even this can approximate if we look at clearly. So we can just uh, okay, I think we are it's making sense now. So we can have t minus half by n, right? Minus e to the power minus t. Okay, but the issue is it doesn't seem to be doing. Let's try some other function. So we want it to have a value of 1, right? So let's try something of the sort of half of uh, say 1 plus of some function which goes to let's try this, tan hyperbolic of x. Now let's see what this does this give us. Now at x, as x is at x is equal to 0, of course it's giving 1. At x it's giving us 1, 1 plus 1 plus it's giving us half. Right? And at x tends to infinity, it gives us the value of 1. So 1 plus 1 at x tends to infinity. So 1, and at x tends to minus infinity, it seems to give us a value of but we can call it to be 1 minus, then of course it's going to 1 minus 1, which is 0. Right? Now we can just vertically shift this to and scale it likewise. Say for example, instead of having half here, just remove the half, and of course so it will be 2, and if you subtract it, then of course we are getting back the same expression, which is tan hyperbolic of x. Right? So it seems that okay, we can construct it in a way, say that you can have tan hyperbolic x minus half, that would center everything at x is equal to half, and then it varies from there to there, like from that. So we can just have something like this. Since it's mimicking everything as n tends to infinity, but the thing is, okay, okay. So we'll try to answer this in the next session. It seems that we are just, but the thing is, ideally we are constructing a sequence such that as n tends to infinity, then this tends to phi of t. So we started with the continuous function, but however we ended up at a discontinuous function, which of course uh, is just a limit, and that is in the limiting case, of course, which will never approach that function. We will be approaching it, but always in a continuous sense, right? So essentially, when we talk about equivalence of functions and sequence, what do we mean? That is the first thing. So say we have a basis for V naught. So that basis is phi of t minus n, right? So all the integer translates of this, and n is an infinite element of the set of integers. This is an expression something like this, from n to n plus 1. And this is an orthonormal basis in the sense that phi of t minus n, comma, phi of t minus m, the inner product of this is going to be 0 for n is not equal to m, and 1 if n is equal to m, where n and m both are integers. Fine. Now we can express any function, say any function x of t, in terms of the linear combination of all this. So say we have say x naught, right, of phi t plus x1 of phi of t minus 1. Likewise, and this side we have x minus 1 of into phi of t minus 1, t plus 1, sorry. Likewise, it goes both ways, right? So this is a way of saying that we can approximate piecewise continuous functions in this form, right? So this x of t is assumed to be some piecewise continuous functions. In general, it need not be, but say we are approximating it. This is more of an approximation, right? So in each term, in each such this one, but we are just trying to approximate in this form at one level of our approximation. So we can go deeper, say we can choose, as we clearly know that we have a general family of such spaces which are denoted by Vm, and this is such that you have phi of 2 to the power m t minus n, right? So this is the family. So where m is also an integer and n is also an integer, right? So this denotes some piecewise continuous function, and this we can clearly write as x of n phi t minus n is equal to minus infinity. So in this case, this is one level of so this is at one level of our resolution, and this is denoted by, of course, at the level where the basis function happens to be. Define the space V naught, right? So we have this n is equal to minus infinity to plus infinity. So what you see is that we of course know this, right? This is just our basis for V naught, and xn happens to be, so xn happens to be the term. Okay. So x of n happens to be the piecewise constants. Piecewise constants. Of course, they are constants or defined over they are constants over piecewise intervals. So essentially, you know what I mean, right? So they are essentially the coefficients of the approximation in the space V naught. So this xn happens to be a sequence. So this we can call it as a sequence, right? And from our condition that xt has to be bonded, right? So this is of course the magnitude of this, but essentially, yeah, this has to be bonded. So this has an analog in discrete sense, right? That the sum of all these absolute this one of the coefficients must also be bounded. So this property we call is that x of t belongs to square integrable space defined over the field of real numbers. Here, x of n belongs to space or square integrable sums, right? Here it was integral, here sums over the field of integers. Right? So that's what it implies. And okay, so furthermore, we said that x of n is the sequence of constants of coefficients, essentially coefficients of expansion with respect to an orthonormal basis of xt. Fine, right? So from now, from this, and we had also learned that say you have xt and yt, both the space V naught, and corresponding to these are the again coefficients of expansion, comma y of n. Then we can have the inner product of xt comma yt is equal to minus infinity plus infinity xt yt dt. And now let's try to get what would it be in, what would this coefficient be? X of n, y of n, right? So we want to understand or derive what the expression for k naught is. And it so happens that k naught depends on the space Vm. Fine. So we had at the outset, we said that x of t can be expressed as a in minus infinity to plus infinity. And we can have xn phi of 2 to the power m t minus n. Likewise, y of t in some other dummy variable p, we can call it x of y of p, phi of in the same space, say 2mt minus p, right? And let's put everything in this. Let's substitute all these expressions in what we have as the L2 product, right, of this function, of both these functions. here x, and then we have minus infinity to infinity, summation of xn, phi of 2mt minus n. Then we have summation over this over n, and the other summation will be over p. So we have yp p of 2mt minus p, and then integrate over where t happens to be the running variable or integration variable, right? And what we can do here is bring both of these signs, both of these summation symbols outside the bracket, outside this integral form. And since xn and yp are scalars and are constants, right? Over piecewise intervals or constant or in that piecewise sense. So you can have xn, yp outside of the integral, and then have minus infinity to infinity for phi of 2mt minus n and phi of 2mt to the power m t minus p integrate over dt. Right? And from the orthogonality property, we have the form of this integral as 2 to the power minus m, right? And if n is equal to p, 0 otherwise. So because of this, it sets a limit on the running variable as well, or it sets us what all coefficients terms we can have in this summation. So in a sense that these two summations would just combine to give us one summation. Say we have chosen n as the dummy variable, and we have xn, yn into 2 to the power minus n. Recall that m happens to be an indication or indicator of the it is the indicator of the space, right? So we can bring it out, just have it n as just a single summation symbol, x of n, y of n. And we were talking about a real signal, so uh, the conjugate of real signal is the signal itself. So just for that sake, to generalize it, let's put a conjugate symbol here, and then this is our value of k naught. Okay. Now let's talk about what we called as the some sort of an approximation. So, and due to the ladder nature, so due to ladder of subspaces axiom, right? We said that V1 belongs to V2, or is a subset of V2, and V1 itself is a subset of V0. There is also some subset of V minus 1, likewise, right? So, since V0 is a subspace of V1, so this implies that if we have, say, V1, then it should be V0, since all V0 are contained in V1, but there is another subspace which is orthogonal to V0, and that we call as W0, right? So V0 is from the ladder of subspaces. We know that V0 happens to be from the ladder of subspace, we know that V naught is a subspace of V1. However, what we see that we require some additional say basis functions, right? Set of basis function, additional space, which when added with V naught gives us the complete space V1. So this is what we call as W naught is what we call as the it's also sometimes known as I think it's known as some approximation space, or I just forgot its name, but it's like there is a space which is orthogonal to V naught. Right? So, and that is how, so whenever if you define, say you have a function, you have some function xt, and you defined it in, say this has been approximated in V naught. Right? So in order to approximate xt in V1, then we would also require it to require another space to account for the error of approximation. Or rather to say, to account for the, rather than error, we can call it the, for the remainder of the signal. And that is where we have this W naught coming to the picture. So the reason is because, so we have V1 in this, in V1 space, this any signal, say xt has, is piecewise constant on a set, on an interval which is n by 2 comma n plus 1 by 2, right? So in a sense that this happens to be in the interval of length half. And you have V naught, which is piecewise constant on an interval n comma n plus 1. So this is an interval of length 1. And so when we, if we approximate some function in, or xt in V naught, then it will have, it will be, or right. So in this case, if you express it in V naught, then it would be piecewise continuous on unit length. And if you would want to further approximate the same function at a slightly more finer detail, then we'll take it to V1, where the signal will be piecewise continuous in half intervals. And we'll just discuss in the next in the next slide. So to fulfill that error, we have this W naught, which is a linear combination of psi of t minus n. So for W naught is where we use our wavelets to, because as we recall that, so wavelets are used as basis for W's. So that is the whole nature of the game here. and any such WM in general, right? Okay, we start with an example. So we have let's start with an example, right? Say x1 t is an element of V naught. Then what happens in this scenario is that our functions will be, say, continuous on this, will be piecewise, it's going to be piecewise constant, right, on this. So that's n to n plus 1. And that is when, even if our signal happens to be in any manner, say something of this sort. Let me use a different color. Say our function is this. So this is our actual function. Let me call it x tilde. And this is, say, xt. I'm just calling it xt just for the sake of convention. I mean, to make our notations consistent. And what we see here is that had we wanted the same function, say x tilde, to be approximated in V1, then in that case, what would happen is that we have this, say, interval. So, and I'll just pick up the same signal, copy it if it's possible. If it's not, I'll just redraw it again. Sorry. So this is our signal, and the interval is n plus 1, n to n plus 1. However, since it's V1, so this supports an interval of half length interval. Rather, this sounds somewhat, it indicates otherwise. So let's call it interval of length half or length half. So we need to have one more tick, right? One more tick mark in this interval n to n plus 1. So let's call it as n plus half. Now in this framework, what would happen is, so we have divided our signal into two parts, and we will have this as the averaged part and this as the, so in a sense, we are approximating it more closely when compared with, right? So this is finer approximation. Right now, and from the axiom of ladder of subspaces, we had V naught to be a subset of V1. So we would want to, since we have approximated in V1 and also in V naught, we want to know what can be done to the approximation in V naught to be able to get the approximation of the signal in V1. So what we would do is, let's have this as x1, and let's call this approximation x. Let's call it x naught, and we'll call this as x1. So in a sense, what we would be doing is x1 t minus x naught t, and that's what we are going to do here. So, and we pick up the same thing. We have this unit interval n to n plus 1. Since our since the difference of the approximation is going to lie in unit length interval, so we would want to have some sort of a wavelet to be able to do that. So in that case, what we do is we look at the difference from n to n plus 1, n plus half, and we see that this approximation, just to let me just superimpose V naught approximation as well. So this is our V naught. So there is our x naught of t. So what we see is that x1 of t is higher than x naught of t. So in that case, we would have a difference which lies here. And we can show that this height is always going to be this height. The reason is because when we take the average of these two, I mean the piecewise constants within the half intervals or within the interval of length half, then we can easily reproduce the interval, the mean for the entire unit interval. So the difference is that, of course, it's going to be higher than that. And likewise, you have, in this case, x1 of t is lower than the mean, which corresponds to x naught of t over this interval. So you'll have difference which lies below. Right? So if it's say if the height is h, then this is going to be plus h and this is going to be minus h. And you can clearly relate it to a Haar wavelet defined on this interval n to n plus 1 and whose height is plus 1, whose height is 1, and of course the values it takes is plus 1 and minus 1, and just multiply this, scale it by h, and behold, you have the basis for the difference between the approximation in these two spaces. And that forms the very central idea of what we do as what we actually say to be. So this is the basis of what we call multi-resolution analysis. So what we do is we start with a finer subspace, with a much coarser space. So idea is we start with we look at the signal, right? So if the signal is like, we look at the variations and try to estimate over what length does the vibration, does this variation uh, uh, really take place, and try to fit it into certain windows of some unit, of some uniform spacing at first. Of course, there are also what I have learned is that you can also have non-uniform spacing. But say you first look at the signal and decide it, look at the variations, and then as an initial approximation, try to get some uniform spacing over which you will be defining the base, the or the course level approximation, right? So here you define some course level approximation. And define some sort of a mean over this. Then you take it further in whatever region. Say in this signal, it so happens that this range has much more variations compared to this length. Right. So let me make it say more. So this is like the variation would be something like this. And in this case, say the variation happens to be small and then somewhere intermediate. Right. So it's in this range. So this segment requires refinement. And this one will do good even with lower or coarser resolution is enough to capture it. And here's some intermediate level of approximation, of course, in a relative sense. So in this case, then what we do is we have already segmented and defined some sort of say this can be approximate to a very well level of detail in just V2, and say this one requires say V3, and this one will require say V5. So what we do is initially we had started with throughout by V0. So this was all V0. Considering that our, let's say, T is equal to, so there's 0, there's still here 1, and from here to here is 2, and till 3, right? So I'm just defining some unit interval of unit length. So in segment 0 to 1, we first found the base mean signal and just call it the constant, say something like x naught of t. And from from 1 to 2 as also we had some corresponding x naught of t. And from 2 to 3 as well, we had some corresponding x naught of t. Then what we saw is from the over the interval 0 to 1, we had to refine one step further using our basis function, which happens to be, so far we have learned about Haar wavelets. So then we use Haar wavelets to accommodate the difference in approximation. Likewise, we repeated it for the intervals 1 to 2 and 2 to 3. And we always kept on checking to what degree or to what level of accuracy are we being able to, so to speak, approximate our signal. Then we saw that we still have some error to cover. Then we did some another level of refinement in this time segment 0 to 1, and then call it V3 or V2. Again, checked it. We went deeper into the wavelet basis for the finer subspaces. Again, approximated it using our Haar wavelets and kept on going. And till level 5, you see that okay, it has been approximated to almost 99% accuracy. Then we could have moved forward, but we chose to stop here. And this one was also done at say 99% accuracy at V2 level. This also say somewhere around 99 or 98.5 accuracy. And this we stop our approximation there because it doesn't make, since these are all we clearly see that there are some continuous signals as the way I have drawn it. So we would require infinite level of infinite resolution to be able to capture it, theoretically to be fully be able to capture it, right? So that's how we actually do our analysis, right? So moving forward, let's discuss about what we had called what we call it to be time filters, or discrete time filters. So what we do here is this filtering business is essentially meant here to be able to project our data or project our signal on a lower basis, right? Or on a coarser grid. So we pass this xn signal to give us an output yn. And so, okay, before that, let's take a slight digression here. So say in V1 space, we were able to, we have the signal, approximation of the signal to be PT. And this has the corresponding coefficients in the V1 basis as Pn. Then like for V0, we have P naught T. There's the approximation whose corresponding discrete coefficient set of coefficients is P naught n. And finally, in W0, we have Q naught T, which is essentially the basis for where we use this wavelet basis, and we have Q naught of n. Right? So that's what. And overall, what we have is P of t. P of t is P naught of t plus Q naught of t. Right? Fine. So when we pass this signal P1 or P, right? So what we see that is we know that Pn will be defined over. So it's like Pn will be defined in such a manner, right? It will be piecewise constants, of course. But say this is from n to n plus 1, and this is n plus half. So this is like n plus 3 by 2. And this we have n plus 2. So it will have this values something like this, right? It will be piecewise continuous or piecewise constants over intervals of unit of half length, right? Or intervals of length half. So you have Pn. However, for P naught of n, they are defined to be constant over unit intervals. So you have this and something like this, right? So to capture the difference, we chose Q naught of n, which are essentially, it only captures the difference of this. So say something like this. So what we essentially wanted to say that is we have P naught of n is going to be equal to P of n, right? So of course you cannot have fractions as you cannot have fractions, right? As our we cannot have fractions as indices. So that's the reason we always choose some sort of expansion such that it's something of the sort of to where say P of I, where I also takes up values such as n 2n 2n plus 1 of this sort, right? So that it's consistent with this. So that's the reason we'll have P of 2n. Let's call this as 2n plus P of 2n plus 1, which is this n half divided by 2. And Q naught will be, of course, equal to P of 2n minus P of 2n plus 1 divided by 2. I think with this, you get the idea what we are trying to say. So when you pass through a filter, the signal will pass through two filters. I mean, it will pass through a filter uh, so as to be able to give us two outputs, right? So one output is what we call as, so say P1, P is passing through this filter. So this filter does two operations. So this is our filter. It does what is called as the decimation, which means it will take two inputs at one time. What I mean by two inputs is like P2n and P2n plus 1, add it up and give it throw out its mean, which is P naught of n. And it will take the difference and throw out Q naught of n. So that's what it is. So it essentially downsamples it. And we call this as decimator, right? This filter as our decimator. So we denote it by lower arrow and 2. Right? And they are somehow related in such a way that we have already seen from. So here n, this n and this n mean slightly different things. Of course, you know from the way it is defined. So we would better to call it as P of I, and where I itself is a function of n, then it makes to be it makes more sense to be able to understand what's going on here. Fine. I think with this, we were able to understand some of the aspects uh, of our filtering business. And of course, the entire we are also able to understand what essentially this filters we call as the filter banks. So they consist of. So right now we are dealing with. So far we have dealt in the class with Haar filter banks, right? And we used this formulation to be able to approximate what we have been doing so far. Then we also defined the Haar in Haar. We did this Haar analysis filter. We use this Haar analysis filter bank in Z domain. So before that, let's try to understand what are the properties of Z. Properties of Z interval we call, or Z transform we call it. So right, so Z transform is a transform applied to discrete signals. It has some properties. First, let's define what it actually implies. So given a signal y of n, the corresponding Z transform will be denoted by y of Z is equal to summation from n is equal to minus infinity to plus infinity y of n into Z to the power minus n. Essentially, that's what it does. And since Z here is a complex number, so for that sort, it is very much analogous to Laplace transfer, not Fourier transfer, right? Because in Laplace transform, we allow the Laplace variable transform variable, which is S, to be a complex number. So it is some sort of similar to that. It resembles more than that of Fourier transform. And this series also converges in a region of Z. So it won't be convergent everywhere. Only over some particular region of Z will this particular series converge. Right? So let's try to derive some properties. First of all, linearity. So Z transform is also it's a linear process, right? It has this property of linearity. So this implies that, say, you have a signal y of n is equal to y1n plus y2n. Then y of z oh, well, you understand the upper and lower limits for the lower and upper limits for the summation operation. So we have n in this to be equal to right. So essentially, you could split it into two additions, and then all that we have is this is a z transform of signal y1, and this is for y2 of z. So this implies that it's linear in that sense, right? Now moving forward, what we would do is let's look at some other properties. Some say property number 2. So if there is some delay in the signal, say n minus d, or if wrote another delay, let's call it shift in the signal. So what we would do is let's if there is a shift in the signal by D, then what would be its corresponding say Z transform, right? So this N, of course, minus infinity to plus infinity. Then you have Y minus D, Z to the power minus D to the power minus D. Sorry, minus N. Now we need to do some change of variables. Let's call N minus D. And D is also another integer, right? So then let's call N minus M as N minus D as some say P. So then this implies that N is equal to P plus D. Also implies that as N tends to as tends to infinity, or is equal to at N tending to infinity, since D will be some finite integer, then even P would be tending to minus infinity. Likewise, at N tends to plus infinity, even P would tend to plus infinity. So it's like the limits doesn't change. So all that we have is you have this to be equal to P is equal to minus infinity, we would call it, and likewise infinity, and we have Y of P Z to the power minus P plus D. And we would use this the distribution of powers, right? So you'll have Y to the power minus P into Z to the power minus D. So you can bring Z to the power minus D since D is some constant. And you would have P is equal to minus infinity to plus infinity and Y of P Z to the power minus P. Right? And you clearly see that this has the same form of, since P is a dummy variable, you can replace it to be consistent. You can just call it N again, since N and P are just dummy variables. And this, you know very well, it's called as, it is the Z transform of Y. So in effect, you have Z to the power minus T minus D. So this also converges at least in a region which is same as the region of convergence for Y of Z, right? So this was one such another such property, and we can go on and on. You can even say describe some property by our own. Say, for example, let's try to there are some properties that say you have Y of N and it's corresponding this to be Y of Z. Then what would be the derivative of Y with Z? For this case, what you would do is Y of t is equal to summation over N Y and Z to the power minus N. So dy Z by dz is going to be equal to summation of N right? Right. So and we can bring the differentiation operation inside. So it's like d by dz of z to the power minus N. So this will give us N Y of N and N into, it's going to be minus of Z minus of N and Z to the power minus N minus 1. And so you can call it as Z minus Z summation of Yn z to the power minus n. Of course, there is n again. So this is how it looks like. So of course, we cannot express clearly in terms of yz because of n coming to the picture, but that's how it is, right? So all the operations will be carried out on z to the power minus n as well. And so these are some of the properties that we had to deal with. And a further question would be, what if the signal happens to be integral over z? But again, that we can just leave it for now because it doesn't um, make much sense as of now to deal with it, right? So right, so this is what it is. And of course, the question still lingering in my mind as to how do we solve this problem here that we are trying to approximate it. So let's pick it up and do something before we move on to MATLAB for our further discussion for today's session. So one function that was coming in my mind was, say, can we do it using sine hyperbolic of x? So since sine hyperbolic of x is given as e to the power x minus e to the power minus x divided by 2, right? And at x tends to 0, or at x is equal to 0, you have sine hyperbolic x to be 0. X tends to plus infinity gives us, okay, it gives us plus infinity, right? So okay, there is where it doesn't clearly answer our question. Okay. So it looks like only tan hyperbolic had such properties that it was giving some finite answers. So let's look at again tan hyperbolic of x. It's just some matter of scaling. Right. So this one was at x equal, it was 0, fine. X tends to plus infinity. It is given to be giving us tends to 1, since this and this, both this e to the power minus x dies, x tends to minus infinity, then e to the power, the reverse happens. So e to the power x dies both the numerator and denominator. So what we are left with is, okay, this is one such thing. Okay, it seems that we are making some headway here. So to be able to center it, say tan of some function, right? So some function f of x, or maybe, yeah, let's start with f of x. So we can have e to the power x minus half minus e to the power minus x minus half e to the power x minus half plus e to the power minus x minus half, right? So in this case, f of x is equal to 0 at x is equal to half, right? Okay, fine. And then the rest of things happen. Fine. So far so good. Okay, so far so good. Now we can parameterize it in terms of this phi of n equal to e to the power, let's call it n of into x minus half. n into x minus half. I think this should solve our problem because let's take a look at it clearly. At x is equal to half, what happens is you have phi n of x is equal to clearly e to the power 0 minus e to the power 0 is just 0, right? So it like, I mean, e to the power 0 minus e to the power 0 is 1 minus 1, so it's 0. Fine. And x at x tends to infinity. Then again, for any n is equal to 4, so here n is always going to be greater or equal to 1. So it so happens that in this scenario you have phi of nx also tending to minus 1. Next tends to plus infinity is phi of n. Fine. Okay, so we are somewhat closer, and let's not call it as phi because we would want to reserve phi for a special purpose. So let's f. Okay. And for the Haar wavelet, we would want to the situation to be such that it goes from t is equal to 0 to t is equal to 1. And of course, we don't care about what it does of below t is equal to 0 and above t is equal to 1. All we care is that's what's going on at half and whether it's able to replicate minus 1. So we have to invert the signs here. That's what it seems, right? Or will that suffice? Let's just take a look here. It was minus 1, right? So if we, okay, so we can call it as phi of n, or in this case, we'll have phi n of t is equal to, if we take minus n of t, minus f of n of t, then it starts to make sense because as uh, t tends to minus infinity, then it will minus 1 into minus 1, right? So it's plus 1. So this is what, so minus, so it's like minus and then plus, so we can have e to the power minus plus e to the power, sorry, minus n t minus half divided by, and of course we can rearrange it, t minus half plus t power n. So initially this function phi n of t would look like something like this at very large value, right? We had some sort of so this t is equal to 0, half, 1, but it would only be say approaching 1 at very large values of t. However, as n tends to, as n increases, so this is say some n is equal to 1. And as we increase n, say this will be for n is equal to 5, closer. So this is n is equal to 5. And furthermore, as we increase our n value, then it will start being very sharper, or it not sharp, it will get steeper at this point. And it will be close to 1 over a longer stretch on this interval half to 1. And gradually as tends to infinity, then phi n of t tends to phi of t. So that's what, just to close this part, right? Okay, so I think I'll be sharing my laptop screen and we'll continue with the rest of the discussion on Haar wavelets and getting to know some of the MATLAB related stuff. So let me just share my screen. Let me share my laptop. Okay. Okay, so it seems I think it's not yet shared, so let me share it once more. Yeah, it's being shared now. Yes. Okay, so I have created this what you would call as the so there's a MATLAB live script, and this has been done with a specific purpose that we can write the text as well as code in the same file. So at first I clear all the variables that exist in this file. And of course, whatever information I am using this code is publicly available on MATLAB's Wavelet Toolbox package website. So we'll start with first understanding or just plotting how this Har wavelet looks in, say, when we visualize it using any such software. So we know very well that Har wavelet is discontinuous. As a result, it's not typically used in denoising or compression active applications where smoothness of the reconstruction wavelet is important. But they do have some superior function, some peculiar properties because of which um, they are used in time localization and also due to their computational efficiency, nature of computational efficiency. So what we do is function, right? And which is say which function is inbuilt in MATLAB's armor. Then we would just use this help command, and then we'll also write the type in the corresponding function that you would want to get some more idea about. So it's help wave function. So what does it do? So it's said that it gives us wavelet and scaling functions, and this MATLAB function returns psi and phi, which are the approximations of wavelet and scaling functions. So psi are the wavelet functions and phi are the scaling functions, right? So Har, and of course both are wavelets, but we just use a different name, right? So scaling functions are the one which we used for our say which are say so for example Har wavelets and all, right? And of course they are similar, so associated with the orthogonal wavelet or the Mayer wavelet. So you give the name of the wavelet, and also uh, what is the second argument we need to give the iter for the number of iterations, and then we just and then we can get phi, psi, and x well. So phi is the, as we learned here, that phi is the scaling function and psi is the wavelet function. So we'll use as, so phi is our approximation, right, or the wavelet function, and will be and psi. So psi is the wavelet function, right? So psi is the wavelet function, and x well it will also give us the value of the function. X is the grid points, and which are right. So that's what it is. So what we did here is we give wavefunk, gave the name of the wavelet as Har, and and asked it to do some iterations till n 10, and the outputs, as we do not want the scaling function, so we only wanted the wavelet function and also the list of points. And then we are able to define or get the discrete the grid points and size the values of at those discrete points, and we just plotted them. So plotted here from over this, right? And we see that it has a value of 1 at x is equal to t is equal to 0, and for t is greater than 1, greater than half, it has a value of -1. Right? And this was our Haar wavelet. And furthermore, we want to say use this data to be able to do something. Let me delete this first part. So we want to do some Haar wavelet transform. So here I just loaded some data which is inbuilt as with MATLAB supplies along with it as in its examples folder. And so this particular data file, it has, let's just, so if we want to execute it, I'll just type in, just press Control plus Enter, and it will be evaluated. So this has sig CLU and signals, this and this as the it's stored in this file here, in this file. So as we learn from the dimensions of both these what do you call variables, for both these arrays or vectors or matrices. So sig CLU is of the dimension 35 cross 1, and signals is of the dimension 35 cross 1440, which means that this is a matrix and this is a vector. So right now we are dealing with a vector, right? So let's just deal with a 1D signal, which is just this vector. So that's the reason I have plotted sig CLU, and this gives us some sawtooth like representation. And what we did here is that I use Haar wavelet to approximate this, and I use this transformation function called Haar t. And when I do this, I get two outputs. So let's also plot this. I mean, get more information about this. So help Haar t. So it does Haar 1D wavelet transform, and this MATLAB function performs the 1D Haar discrete wavelet transform of the even length vector x. So it requires that the vector is even. So that's the reason what you would see is that sig CLU has a dimension 35 cross 1, which means that sig CLU is not of even length. So that's the reason I only took the minimum possible, and while still covering the entire length of the signal. So I just excluded the last element so that we have 34 elements in this, 44 components in this vector. Then I performed this Haar wavelet transform, and it gave us two output variables, which are, or two output entities, which are A and D, right? And I did not prescribe to what level of approximation to do. So that's the reason you'll find only the signal as input I have given. However, this function takes three arguments: x, level, and integer flag. X means the signal itself. Level means to what level of approximation you would want to, or resolution you would want to. And is the data integer in form? So if it's integer, then it will do some special, it will treat it slightly in a different manner, right? So an output, it gives us the approximation coefficients, which are scalar, vector, or matrix, and D is the detail coefficients. So it will give us furthermore about more information about how did it approximate. Right. So here you see that when I type A, enter, it gives us these three arguments, right? And if I say D, enter, so A, it gives us what it tells us that it gives us the approximation coefficients, and D is the detail coefficients. And D, as you see, it's a cell array, and we can access it in different cells, cell-wise in all the elements, right? In the cell-like array, and you find it has multiple entries with a detail level of approximation. To be able to understand this furthermore, we can even ask so just open this in you can just click it. And it says that it gives us. So it says that it gives us the approximation coefficient at the coarsest level returned as a scalar, depending on the level to which the transform is calculated. Scaling coefficients are a low pass representation of the input, divided into coarser approximation and detailed coefficients. The detailed coefficients are referred to as the wavelet coefficients. The number of detailed coefficients depend on the selected level and the length of the input. If D is a cell array, the elements of D are ordered from finest to coarsest resolution. So that's what it does. So that's what it is. And then what I did is I used the inverse Harlan, what do you call this? Since our signal is a very simple piecewise, I mean, they have certain piecewise in a different sense, right? That it has a linear behavior here, linear. So these are all linear signals over different segments. So after we reconstruct it, and I just plot the actual signal and the reconstructed, it so happens that they coincide. And that is very well understood because of the nature of the signal itself. Right? The very fundamental thing is that the signal itself is very simple in nature. So because of which the approximation as the actual signal, they just coincide. So in this, towards this goal, what we can do is let's do some further analysis here. Let's have say x is equal to, let's try to do some transform, Haar wavelet transform of some sine signal. So let's define x is equal to say 0 lin space from 0 to say 4 into pi and with say 100 entries. Then you have y is equal to sine of x plus. Then we can just plot it and see how it looks like. Okay, I should CLF. So there's how it looks like. Your signal sine x, right? And you see it's defined over 2 periods. Now what I'll do is then do this Haar wavelet transform. So we want approximation coefficients as well as the details of the approximation, and do this Haar t of y. And we don't need to worry about the nature of whether it's odd or even, because our signal by the way I have chosen, it is even in number. Okay? So you have Haar, and let's see what it gives. So it's able to do some processing, and it's we can even say, right? Say A is giving this and B is given this 1 into 5. And let's try to say Y R means Y reconstruction. I'll just call it Y rec is equal to I heart and give the inputs A, D. Let's plot it. So hold on. So this was, I would call it as the display name. This was the original signal. And plot x comma y rec reconstructed display name. Call it reconstructed recons. And then legend. Let's press enter. Let's see how it looks like. So even in this case, it's able to fit. The reason because it's able to, because we have given the software the entire freedom to do things by itself. However, ideally, we would not want to do things by its own. So what we would do is we would also give us our own so we would want it to, let's give it some sort of a level, say level 2. And this also constitutes level 2. Let's see now how does it approximate it. Now there should be an error, right? Okay, it says that let's see what is the, why is this error coming? Okay, these I see. So I should not give any arguments here. Oh, it's still able to give us some nice representation. So what if I do at level 1? Okay, let's see what could be the answer for this. Why is it doing it so perfectly? So see level 1, the detail written as a vector or matrix depending on. Okay, so this was, it says, okay, even if you're asking it, what it's doing is it's providing the level by itself. So what if I'm able to give it some other, say 3? What does it show? Hmm. It does it so well. So see if I add some sort of a random into size of x and multiply it with 0.0, multiply 0.3 plus, let's see. Still able to, what if I don't plot? Let's see, still able. It does it so nice finally. specified level. Okay, so it's not something what we expect. It's not doing here level implies something else, not what we would want it to be. We believe it to be, right? So anyway, I'll just get back to you in the next session about this. So let's move forward and look at this example here. So in this case, this again, I took it from the MATLAB's wavelet page. It says that we have a data which consists of two time series. One time series is that of the heart rate of a 66-day-old infant, which is sampled every 16 seconds. Right? For over 9 hours, and the heart rate time series is integer valued. And the other time series is the expertly scored sleep state of the same infant over the same period with the same sampling rate. And the sleep data was scored based on infant's EEG and EOG, which is the eye movement data, and which is not based on the heart rate. And we would want to the sleep rate codes that have been that was defined was one stands for quiet sleep, two is between quiet and active sleep, and three is active sleep, and four is awake. And both the time series were recorded by these professors at some institute, right? Or pediatric institute. And so at first what was done is plot the heart rate along with the sleep states. So we loaded this data, which is available in the examples folder of MATLAB's directory. Then we plotted uh, both this data on the same plot, the ECG as well as the sleep state. So times into HR implies heart rate, right? So left hand side is the heart rate. This blue curve is the heart rate, and this is of course hours, and it has been sampled every 16 seconds, as we can see from here, and it's defined over 9 hours, right? And furthermore, on the right, and we have also plotted the SS, which is the sleep state. And what we see is in the region when the heart rate is very oscillatory in nature, and what we see for 4 is awake. So heart rate is very high when the child is awake. It seems to be correlated. It's like though they are very correlated. As heartbeat falls, which means the child is in deep sleep, right? So when you are in deep sleep or quiet sleep, the heart rate becomes very low, and likewise. So we see that such patterns are visible here, and they are very much correlated. However, what we see, the data is quite noisy because the Harvard transform provides a. It's often useful in situations where a response is dependent on a predictor variable with a small number of discrete states. And here, what we have is that the discrete states for the 4 sleep stages, right? And you obtain the Haar approximation of the Haar data using a level 5 approximation because the heart rate data is integer valued. Right, so we use the integer flag to do all that. So first what we did is we use the heart rate and determined the approximations and the level of details, right? And then we reconstructed it at a level 5 from that data. Okay, it seems that when you use Haar transform, it does at all levels. However, if you want to plot it, right, then there is where you want it to have some special we can define you can reconstruct it at a level of approximation. So let me run this. Control plus enter runs this part of the data, and and this runs this part of the code. So once we have this, so what you see is we are plotting the Haar approximation and the sleep state. So sleep state was Haar approximation of the heart rate. We have plotted along with the uh, sleep state, and it shows that the approximation clearly shows the relations between the sleep state and the heart rate data. And we can now take a look at the correlation between the data. Let's take a correlation between sleep state and heart rate, and it has a I mean, not very much, but it's quite reasonable correlation, which is 0.5576. And correlation of one implies perfect, of course, perfect correlation, right? Uh, so, and if we correlated with sleep state as well as with the reconstructed heart wavelet of the heart rate at level 5, then it gives us a correlation of 0.69, which is quite a bit when you look at the correlation for with along with the noisy data of the sleep state. So yeah, that was what we had wanted to discuss about MATLAB in this today's tutorial session. And in the next session, of course, as the lecture proceeds, we would move on to more sophisticated. Let's learn more of the features about all this. Okay, so with this, I will just maybe close the session for today. I'll stop sharing. And in the next session, let's try to cover all the aspects, other aspects, and all. We'll also do some more programming in MATLAB, and I'll, if possible, I also introduce you to this beautiful package in Python, which is called PyWavelets package. So yeah, let me stop sharing. With this, you can close today's session.